Good morning. This lesson is for my Trig-Precalc class, but before I get started, I want to say I hope that everyone's doing all right out there. I'm not sure how I'm going to title this. I'll title it how I title it in the title. But what I am sure of are two goals for the day. Our first goal is going to be to go over the properties of logarithms. And our second goal is going to be to verify exponential and logarithmic functions are inverses. Well, that they're inverses, sorry. I'm trying to pay attention to a bunch of things going on here. So as we get into our first goal, I'd like to remind you guys about an approach that I had when we were dealing with the sine and cosine function. When I talked about the cosine function, I kept talking about it as the x-coordinate for an angle. And when I talked about the sine function, I kept talking about that as a y-coordinate for an angle. Not only for an angle, but for length for the sine function, that would be the y-coordinate. And then the cosine function would not only be the x-coordinate for an angle, but it could also be the x-coordinate for length as well. So I was hoping by describing those concepts in a different way, we had a better understanding of what we were actually working with. And so I hope to do that again with logarithms. And if we think about logarithms in a certain way, I hope that it allows us to get a better understanding of what we're working with, because for me, dealing with logarithms, it's hard because a lot of things are moving around and it's tough to keep track of. But if I think about what it is and I translate it and I tell it to myself in this certain way, I feel personally I have a better understanding of what I'm working with. So let's just go ahead, I guess, and jump into our first goal, and then we'll move on from there. So anyways, our first goal. We're going to review the definition of logarithm. A equals b to the power c can be rewritten as c equals log base b of a. And remember, logarithms do one thing for us. They allow us to isolate the exponent. And that's so important. They allow us to isolate the exponent. Not very good, E. All right. So there's also one more condition. B has to be positive and it can't be 1. So like I was saying, it's helpful to translate these things. And so let's translate what we see. If I give you c equals log base b of a, to me that means nothing. All right, I'm not following what that means. You know, rubbish. But if I translate it into what it's doing and I say it like that to myself, it means more. C is the exponent B needs to equal A. C is the exponent B needs to equal A. And when I say it like that, it has more meaning to me. And so that's what I want to take as an approach into these properties and investigate and hopefully understand what they mean. All right, so let's move on to our first property. Log base b of 1 means nothing to me. But if I think about it like this, what exponent does b need to equal 1? Then it makes a little bit more sense. Well, any number to the power 0 is going to be the exponent we need, right? So remember, any number to the power 0 is 1. So log base b of 1 equals 0, or the exponent b needs to equal 1 has to equal 0. So that's going to be our first property. Log base b of 1 is equal to 0. Okay, that's our first property. And again, for me, I find it more helpful to translate what I'm working with, and then it makes a little bit more sense. And hopefully you're seeing the value of that. All right, let's move on to our second property. All right, our second property is log base b of b. Again, that means nothing to me when I say it like that. But if I translate it and ask myself, what exponent does b need to equal b? Then it makes a little bit more sense. And in fact, it's the power 1. Any number to the power 1 is itself, right? Because b to the power 1 is b. So the exponent that b needs to equal b is 1. So this must equal 1, and that is our second property. Okay, so when these numbers are the same, it equals 1. When this number is 1, it equals 0. All right? And let's move on to our third property. So this one was hard for me to figure out a way to explain, and I hope I can articulate it in a simple way. Now, this one's different because we're starting off with an equation. So what that means is both of these have the same exponent. Both of these are equal to the same exponent, right? And since they're both equal to the same exponent, that means that b is going to be to the same power, right? So this b will be raised to the same power as that b. And we'll call this exponent, the same exponent, s. Right? So that means that b to the power s must equal m. And this is b to the power s, that must equal n. Well, any number multiplied by itself the same number of times must equal the same thing. So, the last property for this part, there's still one more, but the last property, if log base b of m equals log base b of n, then we can say that m must equal n. So, if log base b of m equals log base b of n, then m must equal n. Right? Because we have an equation, log-based equation, and that means that they're both equal to the same exponent, which means that I'm raising b to the same power, which means that the results must be the same, therefore m must equal n. So let me clean this up, come back, continue with our first goal, and then we're going to jump into the second goal. And again, remember, I need these properties in order to accomplish my second goal. So let me clean all this up and I'll be back. I'm back. So let's go ahead and continue with our first goal. And I wanted to just remind you what an exponential looks like as it turns into a logarithm, and what a logarithm looks like as it turns into an exponential. Right? Remember, logarithms allow us to isolate exponents. Okay, so our fourth property now. Again, I like to translate this. And log base b of b to the x, that means nothing to me. But if I say, what exponent does b need to equal b to the power x, it becomes more obvious, right? And hopefully you understand that it needs the exponent to be x. So our fourth property is going to be log base b of b to the x, or what exponent does b need to equal b to the x? It needs power, or it needs the exponent of x, right? And if you were to rewrite this in its exponential form, you would see that b to the x equals b to the x, right? So that is our fourth property. Let's move on to our fifth property. All right, our fifth property is b equals, or not, b to the power log base b of x. Now, this is not a logarithm, it's written as an exponential, but I think that we can all agree that b to the power of a number must equal a number, right? So let's translate that. B to a power must equal a number. So I can now say, oh, there's a bell. I can now say that b to the power log base b of x, that's equal to a number. I can conclude that. I can conclude that. But now I have an exponential. So now that I have an exponential equation, I can rewrite as a log. So we're going to rewrite as a log. And we now have the isolated exponent, which is log base b of x, equals log base b of the number. Well, we solved from property, I believe it was property 3, because of property 3, which is this guy. If log base b of m is equal to log base b of n, then m equals n, right? Log base b of x equals log base b of the number. Well, then that means that x is equal to that number. So, b to the power log base b of x must be equal to x. That's going to be our fifth property. B to the power log base b of x must equal to x. That is our fifth property. And so now let's move on to a review and examples of each property. And before I continue with that, let me finish this. Log base b of b to the x must be equal to x. And b to the power log base b of x must also equal x. All right. So I have an example of each one. Log base b of 1 means that I need an exponent of 0 to get to 1, right? That equals 0. So 1/2 needs a 0 exponent to equal 1. So this has to equal 0. What exponent does 4 need to equal 4? What exponent does b need to equal b? It needs an exponent of 1. If log base b of m is equal to log base b of n, then m must equal n. I have that situation here. Log base 6 of 10 equals log base 6 of x. So that means that 10 equals x. I can solve equations in this form. Log base b of b to the x. What exponent does b need to be b to the x power? It needs an exponent of x. Right? What exponent does 7 need to be 7 to the third power? It needs an exponent of 3. B to the log base b power of x is equal to x. 3 to the log base of 3 of 1/2. That is 1/2. All right, so I'm going to check off the first goal, going over the properties of logarithms. And again, we need some properties of logarithms, mainly 4 and 5, to verify that exponential and its logarithmic functions are inverses. So I'm going to go ahead and clean all this up, set up the second goal. We'll do some review of what it means to be inverses, and I'll be back. I'm back. So let's go ahead and start our second goal here. And remember, our second goal is to verify that exponential and logarithmic functions are inverses. But before I do that, I'd like to spend a little time reviewing what we've already learned about inverses from the beginning of the school year. So how to verify we have inverses. Remember, inverses lead to identities, and I don't know why I capitalized that, but oh well. Here's an example. 5 plus negative 5 equals 0. 0 is the additive identity. And we call it the additive identity because if you add 0 to any number, you get the identical number back. 1 plus 0 is 1. 8 plus 0 is 8. Negative 1 over 2 plus 0 is negative 1 over 2. You get the identical value back, so that's why it's called the identity. So, 5 and negative 5 are what we would call additive inverses. These additive inverses lead to identities. Remember that. That's a very important concept. Now, in the world of functions, x is the identity. So if functions are inverses, we should get x after we plug one function into the other and simplify. So remember at the beginning of the school year, I was really trying to stress the fact that we can look at functions like numbers. They do things like numbers. They have inverses. They have an identity. And remember, x is their identity. It's a really simple identity because if you have a function like 2x plus 3 and you plug in x, you still get 2x plus 3, so you get the identical value back. So x is the identity in the world of functions. All right, so I would like to just practice verifying identity. So if I plug one function into the other, I should get the value of x back. So remember, we plug one into the other, and we should get the value of x back. So what I'm going to do is I'm going to take this value of x, and I'm going to replace it with this whole value, and let's see what we get when we work that out. Now, if they are inverses, we should get x. So this guy is going to go in there. So now I have y equals 5x plus 2 minus 2 divided by 5. Remember doing this? I think you guys do. Hopefully it's not bringing back some bad memories when we realize, we struggle with this. But a lot of you ended up getting the hang of it eventually. So let's bring this up. And we get 5x plus 2 minus 2 divided by 5. I can cancel out the 2's. Remember, I wanted you to show me step by step how things canceled out, not just cancel everything at once, because you had to show me that you understood the order of operations. All right, so when I plug 5x plus 2 into this function, I got the value of x. So we're halfway there. Now we're going to switch, and we're going to now plug this whole function into this value of x, and we're going to work it out and see if we also get x. So now we have y equals 5, and instead of x, I'm going to say x minus 2 over 5 plus 2, and the 5's cancel. Now I'm left with x minus 2 plus 2, and these guys cancel, and that equals x. So what that means is y equals 5x plus 2. And y equals x minus 2 over 5. These are inverses. Because when I plug one into the other, I get the identity. I get x, because x is the identity in the world of functions. So I just wanted to quickly review with you guys what it meant to verify identities before we started the second goal with actual logarithmic functions and exponential functions. So I'm going to clean all this up, set up the last part of the last video for the last goal. So let me clean this up and I'll be back. I'm back for the last time, I promise. So let's go ahead and finish this second goal. And as we get into verifying that logarithmic functions and their exponential counterparts are in fact inverses, I needed to review with you the fourth and fifth property from today's lesson in the first goal, because we needed these to verify inverses. Alright, so remember log base b of b to the power x is equal to x, and if we translate this, it's saying b needs the exponent of x to become b to the x. And this one, I always struggle with this one. This one always gives me a hard time, but when we rewrite this as a logarithm and isolate the exponent, we see that this value, in fact, has to be the value of x. So b to the power log base b of x must equal x. So whatever that value there is what this has to equal. I always struggle with that one, but I remember I have to use the rule to get to that point. All right, so let's go ahead and move forward. Find the inverse of y equals 5 to the power x and verify. All right, so remember when we find inverses, we switch the x and the y. And by the way, this is what your homework will be about. Okay, we switch the x and the y, then solve for y. Alright, so y equals 5 to the power x becomes x equals 5 to the power y. We rewrite as a logarithm because remember logarithms allow us to isolate exponents. So we get y equals log base 5 of x. And this is the inverse function to this, hopefully so. And we are going to see when we plug one into the other. Right? So let's verify. So I will start with this function first. Y equals 5. And instead of x, I'm going to put a parenthesis, and I'm going to plug in this other value. And now I have log base 5 of x. Well, guess what? I have the fifth property. 5 to the power log base 5 of x. These are the same, so that means that this value must equal that by the fifth property. Okay, let's switch the order and start off with the inverse. And we have y inverse equal to log base 5. And instead of x, I'm going to put 5 to the power x. But guess what I have now? I have the fourth property, which says that this base needs an exponent of x to turn itself to the power x. So that means that we get this equal to x by the fourth property. And therefore, we have inverses. Where did it? Oh, there it is. So I'd like to try one more problem, just a little extra level here. Let's see if we can find and verify inverses. So if I gave you the problem y equals 3 to the power x plus 2, let's find the inverse. So the first thing we're going to do is we're going to switch the x and the y. So now this becomes x equals 3 to the power y plus 2. We're going to write that as a logarithm. So now we get y plus 2 equals to log base 3 of x, but y is still not by itself, and we'll get there by subtracting away the 2. So now we get y equals log base 3 of x minus 2. That should be the inverse of this. And again, let's verify. So I'm going to write y equals 3, and I'm not going to put the power x, but I have to put the plus 2, and I'm going to replace the power x with this. So I get log base 3 of x minus 2. Not this, I'm sorry. Let me redo this a little bit better. I'm sorry. I'm a little bit rushed and flustered. I apologize. All right. So I'm replacing this with that x. Now I can eliminate the parentheses, and again I can cancel this out because minus 2 plus 2, that goes away. And now I get y equals 3 to the power log base 3 of x. And again, we've got the fifth property, and so I can replace that whole thing with x. All right. So let's just verify the other side, but before I do, I want to make sure I have room because I would hate to have to record this again. And I think I can squeeze it in right here. We'll verify the other one. right here. So I'm going to start with this guy. Y inverse equals log base 3, and not an x, minus 2. You know, I'm going to move the camera over just a hair, because I'm going to fall off the screen. Oh, I'm really flirting with it. There we go. Okay, I don't want to have to record this again. I don't want to have to record this again. Okay, so in here goes this. All right, this is the fourth property. So whatever my exponent is what this turns into, so this becomes x plus 2 minus 2. The minus 2's and the plus 2's cancel, and that's equal to x. So because they're both equal to x, that means that these are inverses. Let me circle that. These are inverses. All right. So I will be adding a little extra to the problems. Make sure you pay attention to the order in which you untie these things. That's going to be very important. I'm going to go ahead and end this lesson here. I think I'm satisfied where we ended up. Again, I hope everyone is doing all right out there. Have a great day, everybody. Bye-bye.